Welcome to our lesson on implicit differentiation. So before we get into what implicit differentiation is, we should probably talk about just that word, implicit. What does implicit mean? So actually, best way to sort of see that is to sort of look at the contrast. Normally, functions are defined explicitly. So, for example, y equals x squared, or you'd write f at x equals x squared. So here we'd say y defined explicitly in terms of x. So y is defined, as a thing with x in it, but it's explicit because y is by itself here. So we have y alone on one side of the equation. Y alone on one side of the equation. And then the other side of the equation is all x's. And then sort of by contrast, sometimes we have relations. So implicit would be something like or would be exactly something like this: x squared plus y squared equals 4. So here x and y are said to be defined implicitly because we don't have y equal to something or x equal to something. But if you gave us an x, you could figure out the y, or if you gave me the y, you could figure out the x. But you'd have to do some rearranging. So here we'd say x and y are defined implicitly. So that just means that they're not alone on one side of the equation, or they're not explicit on one side of the equation. So, well, let's do this example. So our goal will be to do it. So implicit differentiation might sound like you're going to try to find the derivative of something like this. So how do we find the derivative of something like this? Well, we know this isn't a function, right? It's a relation, relationship between x and y. It's actually a circle with radius 2. So not a function because it doesn't pass the vertical line test. Each x does not have a unique y. That's a terrible circle. So how do we find the derivative of something like this? Well, one way find x explicitly. So just rearrange y squared equals 4 minus x squared, and then y would equal plus or minus 4 minus x squared. So there's two pieces here. The positive piece, y equals, and then over here the negative piece. So this is the top half of the circle, and this is the bottom half of the circle right here. And then you want to find the derivative, so dy by dx. So we know that's 4 minus x squared to the half, so 1/2 4 minus x squared to the negative half times the derivative of the inside minus 2x. 2's are sort of reduce, so we'd have minus x over square root of 4 minus x squared. So that's the derivative of the top. So the derivative of the top of the circle, right, this was for the top, would be this. And then the derivative, that's the derivative for the top. Then the derivative for the bottom, you have to do the same thing. I won't write it down, but I'll just, that would be equal, it's almost the same, it's just now there's no negative. You could do all the calculations to see that that's the case. So that's the derivative for the bottom. So we get two different derivatives. So we can get the derivative of something like that. But would it be possible to do this question if we didn't first isolate for y? So let's say x squared plus y squared equals 4. Can we get dy dt? So dy dt is our goal. What do I say? Getting ahead of myself. Dy dx. dx. So what is dy dx? Well, what we're going to do is take the derivative of the left side and take the derivative of the right side with respect to x. Okay, the right side, that's easy. D by dx of 4 is, that's a constant, that's 0. Now I'll apply my sum rule, so I can take the derivative of the first plus the derivative of the second. Well, d by dx of x squared, I know that, that's my power rule, 2x, plus, and now this is sort of where something's different's going on. Your first instinct might be, okay, the derivative of y squared 2y, and that would be a lot of people's first instinct. But the problem is, this is an x and this is a y. Those are different variables. I can't differentiate y, a function of y, with respect to x unless I do something first. So here's how I like to think about it, or like to explain it. Think about, even though we didn't just explicitly define y in terms of x, y is equal to f at x, we had the y and the x together. Imagine you did. So I'm differentiating y squared. So that means f at x squared. Well, if I want to differentiate both sides with respect to x, I have to differentiate f at x all squared. Well, how do I do that? That's a power of a function, right? Or the chain rule. So remember that that's equal to 2 f at x, but then you have to multiply by the inside derivative, or f prime at x, which in this case would be 2, and then f was equal to y times f prime, which we could say is dy dx. So the derivative of y squared with respect to x is not just 2y, it's 2y times dy dx. So you have to do this sort of extra step of multiplying by a dy dx. And then I'll divide everything by 2, and then isolate, well, okay, x plus y dy dx equals 0. And then I'll isolate for dy dx, because that's what I was after. So dy dx equals negative x over y. So the derivative of, or dy by dx of this relation is equal to this. So notice that my derivative is now defined implicitly, which makes sense since the original relation was defined implicitly also. And there's actually far less calculations than that other way, right? We didn't have to do any chain rule or anything like that. And it's a much sort of neater, simpler formula or equation. So, this seems pretty good. Okay, we'll just do one more example. And this example is slightly different than the last one. So you remember the last one? Well, probably it was 2 seconds ago. I think it was x squared plus y squared equals 4. And we said, we showed how to do it implicitly, but we said you could do it by solving for y first, and then just doing the regular derivative explicitly. But notice with this one, this is a weird relation. I have no idea what this looks like. This is some kind of weird relation. You couldn't solve for y first. There's no way to isolate, well, there might be a way, but it would be very, very difficult to find y by itself, right? Because there's a y and a y squared. So you're going to have a tough time differentiating explicitly, or defining this implicitly in terms of y. So really our only option here is to do implicit differentiation. So that means we want dy dx, so we're going to differentiate both sides with respect to x. So let me differentiate each of these sums with respect to x. And the derivative of this is 0. Okay, the derivative of 2x to the 4 would be 8 x to the 3 plus, now notice this is the derivative of 3x squared y. That's actually a product, right? 3x squared times y, so product rule. So I'm going to do the derivative of the first, which would be 6x times the second, plus, leave the first, and then the derivative of y with respect to x is dy by dx, plus, now the derivative of y squared with respect to x, same as before. You'd think it's 2y, but then you have to multiply by dy dx because it's really the chain rule. So just think about what we did in the last example. It's the y you have to multiply by dy dx in both of these. So now we're just trying to find for dy dx. So let's kind of group them or add like terms. And then this will subtract from this side. So appear on the other side. So we're going to factor out a dy dx from these two terms. So we're going to have 3x squared plus 2y. I subtracted this, so negative 8x cubed, and I subtracted 6xy. And then to get dy dx by itself, so there is dy dx, or the slope of a tangent at any point. And again, the derivative is defined implicitly, but that makes sense because the function was to, or the relation was to.